So, second to last section, it's about the divergence theorem. Before we state what that is, let's recall first that...
Does that have something to do with curl?
No.
That's next.
That's next unit, yes. Recall that given a vector field f of x, y, z equal to f of x, y, z, I'll just continue, y of x, or g of x, y, z, h of x, y, z, sorry about that, that the divergence of the vector field was partial f partial x plus partial g partial y plus partial h partial z. So we learned about divergence, I think either the first or second day of the unit.
I think it was first. No, wait.
I don't know if it was,
Second.
yeah. We talked about how to calculate it and how it dealt with fluid flow. Okay, so that's pretty much what you should know about divergence coming in. Here is the divergence theorem. Let G be a solid whose surface is oriented outward with n being a outward unit normal on the surface. Then we say that the flux, so let me kind of make an analogy here. When we did line integrals, we had a direct way of computing them, and if there were several paths, we had to do several line integrals, or we had a special case where if it was a path that was closed, we could use Green's theorem, right? This is kind of like that, because in 15.5 and 6 we dealt with flux integrals, which were really surface integrals, and the surface usually was not closed. You know, you had like a paraboloid, and or you just had part of a surface. If we look at specifically a closed surface, then we can apply the divergence theorem, which says that the flux can be calculated using a triple integral of the solid represented by G of the divergence of the vector field, dV. So flux for a closed surface, which is a solid, you can use the divergence and do a triple integral and then calculate it that way, which can save a lot of time. Now, in the interest of finishing this before you guys get out of here not having homework over break, we're going to skip the proof, which is a page and a half. It's a shame. And we'll just go straight to applying this. If you want to see the proof, it's in the book. I could make a video later if you guys want, but okay. So here's an example of using the divergence theorem. Find the outward flux of the vector field f equal to x, y squared, z across the surface S, where S is the tetrahedron bounded by 2x plus 2y plus z equals 6 in the first octet. Okay. So if we draw a picture, x-intercept and y-intercept is 3, z-intercept is 6. Anyway, we have 1, 2, 3, and then a fourth surface. If we were to find flux, there would be 4 surfaces we'd have to take into account. Does that make sense? So the old-fashioned way, we'd have to say that the flux would be a surface integral of 4 surfaces. And you can call them whichever one is sigma 1 or sigma 2, but bless you. Okay, and no one wants to do that. Now, the divergence theorem tells us, and again, the condition that we need in order to use the divergence theorem is that this is a closed solid, which it most certainly is. It says that we can calculate flux by doing a triple integral of the divergence of the vector field and then just plugging in the bounds of the solid into the integration. So let's go ahead and set that up, and then I'll let you guys work through it. Divergence of this vector field would be what?
1 plus 2y plus 1.
Let's go dz, dy, dx. If we're going z first, z is going from
0 to 6 minus 2.
Yep. So solve for z up here. 6 minus 2x minus 2y. And now for the... Did I just write dz twice? Yes, I did.
So did I.
That's why you don't listen.
I wasn't looking.
That's why you're listening. Because I actually said it right.
That's why you do. That's why you. No, but sometimes you say it wrong. And you
I know, yeah.
Really? Oh.
Yeah.
All right. dy would be from 0
3 minus x.
to 3 minus x. And x is from 0 to 3. Take a few minutes. Work through it.
In the spirit of the Odyssey. Wait, what did you think it's cute if you don't want to. And go get the cube thing next time.
There's a lot of time. I know.
Yeah, it's long either way.
Yeah, it is kind of...
Can we just trust you?
Well, we haven't done one in a while, so... I'll just make sure that you
This
guys.
is the longest one possible.
Yeah. Why not?
Yeah, it seems
Yes,
like it.
they're
Yeah, everyone loves candy cane. Did you not bring your own candy cane?
Yeah, I guess.
What's that?
He didn't bring his own candy cane.
Just
J-Rock.
out of the
That was the prerequisite to get into class. You must bring candy canes to Calc 3.
The one they don't break in.
Yes, you have to learn the proof.
Okay, this is disgusting.
Yeah, I'm not feeling this either.
I know it's
Yeah, I got this one.
Can you just tell us the answer so I can do that?
I switched dy dx to dx dy at some point.
Awesome. Just solve for dy.
That might save some time. And I avoided multiplying stuff out until I really needed to.
I'm just gonna wait for
Yeah,
these.
but I'm at the part where you have to multiply things about.
I don't have any space.
Extra candy cane for the first person who finishes. That's the right
It's
answer.
gonna be 0.
No,
Wait,
it
I'll
can't
look
be.
in the book.
It
7 over
can't
2.
be.
Is this the same column in the book?
I don't know. Sometimes I use the same one. Sometimes I pull them from other places.
I'll tell you the answer. Give me a second.
Carl, when you get it, don't say it. Oh no, that's another minus. I'm slightly close.
The one in here is a lot easier, just saying.
So I didn't use the one
I
that was in
know.
there.
This one's like a 2-step one. It was like a 20-step one.
Does anyone have that thank you? Yeah, I got it down to here. So, I just can't have very much. Hello, hello. Thank you for joining us. Did you bring our candy cane today?
Did you bring your own
I told you you're the only one.
I know, right?
Only one. How dare you. I solved it.
Must have been one of those
Is it
times where
negative
J-Rom
135?
came in late where we mentioned.
Is it negative
Yeah.
135?
No.
Oh wait, I could just plug this in my calculator. No. I have no idea.
I'm just waiting for
I hate this. Are you sure?
Yeah.
Maybe you did it wrong.
No.
Maybe he did it wrong. Wait. Is it negative 189?
No.
Dang it. Is it negative or positive?
It's positive. I can tell you that much.
Is it 22.5?
That's closer, but no.
God dang it. So I made at least 3 errors. Can you believe this? Addie, I can't
These
believe it.
3, like,
The
I'm
answer's
guessing
24.
Final?
That's his average.
24.
No.
I'm just gonna guess numbers.
I'm just going to do 0.5.
I already thought that one.
Yeah. Where did I go wrong? I think that's a question that we all need to ask ourselves. Where did we go wrong?
Still waking up this morning.
Yeah, just pause when you start.
oh, so you answered when you started
Yep.
this class. So.
Oh, yeah, I picked up again. That's what you get when you're in classes, for example. Oh, Mr. Pierce isn't here.
Is it 140?
Really?
Yeah.
No.
Stupid people, they would just point out the.
I don't know the formulas for the
No.
What?
And he said that like Chris knew he wasn't going to be here for the past few days.
Oh, really?
Yeah, this is
Okay, that's
But he just
Is it
didn't
31.5?
It is 31.5.
Why didn't you say it? Come on.
What was your
Did you actually work it out?
No, I just put it like
And you did the same.
What's wrong with that?
What was your final integral?
Absolutely nothing. Oh, my final integral? I made at least 3 errors.
Hey.
I'm guessing 3 errors.
Mulan and I are like reverse color here.
It is 31 and a half.
I like it.
dot, 31.
Okay.
Since you will be doing a few triple integrals on the exam when we come back after break, I'd recommend going back and actually trying to work it out so that you get 31 and a half. Let's do one more, shorter one. And then we'll talk about some concepts and we'll call it a day.
Or a year.
Yeah, I guess that's true.
Dang it. What was the answer?
31.5.
That's not error. It's not error.
Find outward flux.
Did you guys get a hint?
No.
They can get it on the way out.
Hold on.
Through the sphere, they're still working on the other one.
No, I didn't say it.
X squared plus y squared plus z squared equals 4. For the vector field, f equals 2x cubed, 2y cubed, 2z cubed.
Yeah, we could just use the thing. I don't even know how to speak anymore.
Use what thing?
Spherical substitution.
Eventually, yes, spherical is going to make it really nice.
Oh, so we should use spherical cuts?
You will. We will. Okay, so the flux will be calculated using a triple integral. And again, a couple of you actually were asking about like switching to spherical and stuff and cylindrical or polar. Always set them up the way that we've been doing them. So either, well, in this case, we all have done rectangular, but like in the flux integral section, you either set them up parametrically or rectangular, and then maybe you switched to polar or one of those options. Try not to like switch to polar right away, because then it gets really confusing as to what the surface area formula should be when you calculate it. Because it becomes like partial vector r over partial r crossed with partial vector r over partial theta, and anyway.
That's awful.
Set it up first, and then if it presents itself as something that you can switch, then do it. When you find the flux here, or the divergence, sorry, you get 6x squared plus 6y squared plus 6z squared. Let's pull out the constant. And then we have x squared plus y squared plus z squared. Which, yeah, let's switch it to spherical. X squared plus y squared plus z squared is rho squared. dv translates to rho squared sine phi d rho d phi d theta. And our original surface, so now that's what we're going to use in the bounds here, right? It's just a sphere of radius 2. So that means rho is from 0 to 2. Phi is from, yep, and then theta. Good. All right, so let's see. We get 1/5 rho to the 5th. You could. Whoops. And rho is from 0 to 2. Plug in 2, you get 32/5 sine phi d theta. So that's 192/5 if you pull it out. And then the integral of sine phi negative cosine phi from phi equals 0 to pi. That's 2. That's negative 1, so 1 minus negative, yeah, that's 2. And then 2 theta, 0 to 2 pi, so multiply by 4, 768 pi over 5. That one was more fun. Okay. Here's the last thing that I wanted to mention. Sources and sink. Or sinks. Sources are points where fluid enters flow. Sinks are points where fluid leaves or drains the flow. Certainly does. And it's tied to divergence. The divergence has to be positive. So if we evaluate the divergence of the vector field at a point, if it's positive, we know it's going to be a source. And if it's negative, that means flow is leaving. So it's a sink. That's it. That was a long proof I cut out.
Did you want to do that?
Are there any questions? No, it's going to take like 25, 30 minutes.
25 minutes.
Yeah, usually I do this lesson in 2 days.
Oh my god.
What is the benefit of doing the proofs? Is it just to know where the equations derived from?
That's one of the benefits, is to know where everything comes from. The other would be, for those of you that are